In this video, we're going to continue doing examples of trigonometric derivatives. This is part 3 of the video series for derivatives with trigonometric functions. So let's look at this example. If g of x is e to the x times cosine x, find g prime and that's a comma, g double prime. So I see e to the x, there's an invisible times there, right? So then we're going to need the product rule here. So we're going to say g prime of x is, product rule tells me is the derivative of the first, so d dx of e to the x times cosine x plus the first, e to the x times the derivative with respect to x of the second. And so g prime of x here, let's take the derivative. The derivative of e to the x is just e to the x cosine x. And here we leave e to the x alone. And the derivative of cosine x is negative sine x. Now here, right, we're multiplying. So let's rewrite this. E to the x cosine x, positive times a negative becomes negative. So negative e to the x sine x. And can we simplify? Yes, we can take out the e to the x that appears to be a common term in both of those terms. So e to the x, and take it out. So I'm left with cosine x minus sine x. So then this is the first derivative. So I know this wasn't stated in the question, but what if I wanted to find the x values where this has horizontal tangent lines, where g has horizontal tangent lines? How would you do that? I have the derivative, right? So then in order to answer this question, I would set the derivative equal to 0. So in this case, g. So I will say e to the x times cosine x minus sine x equals 0. So either e to the x is 0, we know this can't happen, or cosine x minus sine x equals 0. So this is whenever sine and cosine are the same, right? Where cosine x is equal to sine x. So this happens when x is pi over 4 in any multiple of pi over 4. So they are the same at pi over 4, and where else are they the same? When they're equal to 1, they're going to be when tangent is equal to 1, right? Another way you can think of this is that divide both sides by cosine, so you'll have 1 equals tangent x. So tangent is positive in the first quadrant, so that's pi over 4, and it's positive again in the third quadrant, so that will be at 5 pi over 4. And then any multiples of 2 pi from that. Okay, so that was a slight tangent. So the question here was, no pun intended with the tangent line there, find g prime and g double prime. So we found g prime. Now to find g double prime, so the second derivative, so the first derivative gives the rate of change of the function, right? First derivative is the velocity function, so the average rate of change. The second derivative gives us the acceleration. So second derivative is the acceleration function. Third derivative gives the jerk of the function. And so let's do second derivative here. Now it is helpful to simplify the first derivative, so that notice here I have e to the x times this quantity. So I only have to use the product rule once. If I left it unsimplified, I have e to the x times cosine x and e to the x times sine x. So I will have to use the product rule twice. So it's easier when I fully simplify it, because then I just have to use the product rule once. So let me just write out again what our derivative was, which is e to the x times cosine x minus sine x. That's our first derivative. So then the second derivative, I'm going to use the product rule again. So product rule says the derivative of the first, so derivative e to the x times the second left alone plus the first left alone times now the derivative of the second function. the cosine x minus sine x, and then we find this derivatives. The derivative e to the x is just e to the x, so it stays the same. And the derivative now here, the derivative of cosine is negative sine, and the derivative of sine is cosine. So I have this. Let's see, are they the same? No, not quite. So we can factor out the e to the x. I could probably factor out a minus also, so we'll do that as we go. So take out an e to the x, and I'm left with cosine x minus sine x here. And if I take out this minus from this quantity, I'm going to have minus, well, hang on, we're taking out the e to the x, so I'm just going to have minus sine x and then minus cosine x. So combine like terms, what do we have? So the cosines are actually going to zero out. Cosine x minus cosine x is 0. And I have negative sine x minus sine x, so I get minus 2 sine x. So I'm going to have e to the x times a negative 2 sine x. So I can write it as minus 2 e to the x sine x. So this is our second derivative. So this gives us the acceleration function. Okay, now let's try some applications. So we have this example. An elastic band is hung on a hook and a mass is hung on the lower end of the band. When the mass is pulled downward and then released, it vibrates vertically. So imagine you have a rubber elastic band hanging down, and then you pull it downward and then you release it. So it's going to vibrate, and it says vertically. So the equation of motion is S equals 2 cosine t plus 3 sine t, where t is, greater than or equal to 0. So positive. And S is measured in centimeters and t in seconds. The first part is asking us to find the velocity and acceleration at time t. So for one, the velocity function is the derivative of the position function. So in this case, the derivative, since our variable is t, is d dt of the position function. And the acceleration is the derivative with respect to t of the velocity function, which then in turn means that it's the second derivative of the position function. So it will be second derivative, so it's d squared, right, of the position function over dt squared. So this is the notation for second derivative. I guess I could also say the velocity function, right, this is s prime of t, and then here the acceleration then will be s double prime of t, so the second derivative. All right, so for the velocity function, so v of t is, as I just said, the derivative of the position function. So recall, what is our position function? S is equal to 2 cosine t plus 3 sine t. So that means this is the derivative of 2 cosine t plus 3 sine t. So take the derivative of that. So our velocity function is the derivative of cosine is negative sine. So this is minus 2 sine t, and the derivative of sine is cosine, so plus 3 cosine t. So that's our velocity function. Now the acceleration function is the derivative of the velocity function. And so in this case, the derivative of sine is cosine, so I'm going to stay with the minus 2, not cosine t, but the derivative of cosine here is negative sine, so it'll be minus 3 sine t. So now we have our velocity function and our acceleration function. What is the second part of this asking? When does the mass pass through the equilibrium position for the first time? So equilibrium position is essentially back when the position where it started, so when S is 0. So when does the mass pass through the equilibrium? position for the first time. So this will be when the position is 0. So that means we want the position s of t to be 0. So set the position function equal to 0. So I'm going to have 2 cosine t plus 3 sine t equals 0, and then solve for t. This might not give us a nice reference angle because I see that I have 2's and 3's there, but let's still solve for it. So I'm going to leave the 3 sine t over here and move the cosine over. Or actually, let's leave the cosine here and move the sine over. So 2 cosine t equals negative 3 sine t. And what I want to do is get a tangent in here. So divide both sides by cosine t. So I'll have 2 equals negative 3 sine t over cosine t. So there's my tangent. And divide by negative 3. So I'm going to have minus 2/3 equals sine over cosine, which is really tangent. So as I mentioned earlier, right, this is not a reference angle that we know. There's nothing that tells us, well, tangent of that angle is negative 2/3. Like we know when tangent is 1, when tangent is √3/3, or just √3. Those are our standard reference angles. So here, let's bring in our inverse tangent. So then t is going to be the inverse tangent of negative 2/3. Now the problem with this is that this is going to give us a negative answer. So when you put it in your calculator, right, because of the range of inverse tangent, this is going to give us a number. The range of inverse tangent gives us between negative pi over 2 and pi over 2. So because this is negative, it's going to give us a negative answer. But t is time, so time can't be negative. So let's make sure that our calculators are in gradient mode and put this into your calculator. So what you should get is negative 0.5880 is t. Now, looking back at the problem, right, it said that t is greater than or equal to 0. And so because t is representing time, so t is in seconds, so we can't have this answer. And so we just have to convert it to something that is greater than 0 and is coterminal. So we know that tangent is a periodic function, so tangent x has a period of pi. And so add pi to this. So RT will be really the negative 0.5880 plus pi. Again, make sure you have your calculator in radian mode when you do this. And now add pi, and we'll get t equals 2.554, let's say, to 3 decimal places. So that means that this band is going to go through equilibrium for the first time after 2.55 seconds. Okay, so I wanted to do an example like this to illustrate that because when we have to bring in an inverse tangent, we are restricted to the answers between negative pi over 2 and pi over 2, but then you just have to adjust based on the period of the function. So if it was sine or cosine, the period of those functions are 2 pi, so you have to adjust by that. And in this case, because it's tangent, the period of tangent is pi. All right, so after 2.55 seconds, this band is going to pass through equilibrium again, so meaning its original position. So let's try our next example. So another application problem, we have a ladder 12 foot long resting against a vertical wall. Theta is the angle between the top of the ladder and the wall, and x is the distance from the bottom of the ladder to the wall. So if the bottom of the ladder then slides away from the wall, how fast does x change with respect to theta when theta is pi over 3? All right, so there's a lot going on in this problem. But I realized that there's a ladder, there's a vertical wall, and we have an angle. So I'm going to draw a picture. What picture would you draw? Based on the fact that we have a vertical wall and then a ladder leaning against it at an angle, I'm inclined to draw a right triangle. So let me bring in a right triangle in here. All right, so now that I have my triangle here, we have the 12-foot ladder is over here. So this is the ladder. And then it says theta is the angle between the top of the ladder and the wall. So theta is over here. This is our vertical wall. And what else do we know? X is the distance from the bottom of the ladder to the wall. So bottom of the ladder is over here. The wall's over here. So this must be X. Okay, what are we trying to find? So always with word problems, I say focus on what the question is or the task. What are you supposed to be doing? So the question here is how fast does X change with respect to theta when theta is pi over 3? How fast does X change? So what is that a measure of? How fast is velocity? Right? So essentially we want to find how fast is X changing. So what is the velocity when theta is pi over 3? So I need to get my hands on the velocity function. Well, I should probably get my hands on the position function to begin with. So because I have a right triangle, we can create our function with this right triangle. So I want to incorporate theta, X, and that constant, 12 feet, into a function. So what function do I have here? That incorporates so theta's over there, so this is the opposite, and then the hypotenuse. So what trig function can you think of that incorporates an angle? Is opposite side and then the hypotenuse. Sine, right? So we can use sine here. So I can say sine of theta is equal to the opposite, x over hypotenuse. So x over 12. And now it does say how fast does x change with respect to theta. So I really want a function to be with respect to the variable theta. So multiply both sides by 12. So I'm going to have 12 sine theta equals x. And so here's my function. So now, since I want to know how fast does x change, so I want to find the rate of change of x with respect to theta. So find dx theta. So take the derivative of both sides with respect to theta. So I'm going to find d theta of 12 sine theta and d theta of x. So here I just get my dx theta, which is what I'm looking for. And here I take the derivative. So 12 sine theta, the derivative of sine theta is cosine theta. So I'm going to have 12 cosine theta. Now it says to find, so now this is my rate of change, the rate of change of x with respect to theta at any point, and I want to find it when theta is pi over 3. So when theta is pi over 3, what is dx theta? So the rate of change of x with respect to theta then is going to be 12 times cosine of pi over 3. And so what's cosine of pi over 3? Cosine of pi over 3, look up your unit circle or the little chart that I have shared with you, or draw a triangle, but cosine of pi over 3 is 1/2. So then the rate of change of x with respect to theta is 12 times 1/2, which is 6. And what are our units going to be? Let's see, where we're given units, feet, and then theta is in radians. So then this is going to be the rate of change of x, which is in feet, over the rate of change over theta, which is in radians. So this is going to be 6 feet per radians. And that will be my final answer. So the rate of change of x with respect to theta, 6 feet per radians. All right, I hope that this is helpful, and email me if you have any questions.